Afternoon is Martina Hofmanova, and we will have 543 constructed via PDEs.
Thank you. Thank you very much for the introduction. Also, many thanks to the other organizers for having me here. So what I want to present to you today is a new result that we obtained together with Massimiliano Gubinelli. You can find it on arXiv. And in this paper, we give a new construction of the Euclidean Phi 4 quantum field theory. Now, we have already heard during this workshop that, well, this measure, as I will also tell a little bit more about it, well, this has already been constructed many times. Many people contributed to that. Some of them are also in the audience, and I was happy to meet them here. So the question you might have now is, why do we need yet another construction of this measure? And the point is, well, this construction is very different from all the previous constructions. It uses the new and old PDE techniques. So we take a totally different approach. We study the stochastic quantization equation, and we use some PDE methods in order to construct this measure. I also believe that this approach is rather simple, but we have already understood that everyone believes that their method is the simplest possible. So, well, you may want to decide this yourself. Okay, so what are we actually interested in? The Euclidean quantum field theory, the Phi 4 quantum field theory, this is a probability measure, namely a probability measure on the space of distributions on R3. And this measure can be formally written by this expression. So this is something that we have already seen here before, and you also immediately see that this doesn't actually make any sense, right? Because here what we see, well, that's like an infinite product of Lebesgue measures, and we know that this does not exist. Okay. On the other hand, we see, well, some positive mass, m squared, positive coupling constant, lambda. But if you think about this formula, you recognize here these two terms. This actually gives you a Gaussian measure. Namely, that's the law of the Gaussian free field. And this is now a well-defined measure on an infinite dimensional space. Okay, so you might want to rewrite this formula, take this out of the density, and only this would be in the density, and there would be the Gaussian measure. And so you might think this maybe solves the problem, but of course then you realize very quickly where the support of this Gaussian measure lies. Namely, it lies in the space of distribution, so really these are not functions, and you see a problem here in building the fourth power of a distribution. So we have already heard about these difficulties, and this is what makes the problem challenging and difficult. Yeah. Okay, so now, well, you actually are not sure what measure you should construct, because I give you a formula which doesn't make any sense. So who decides that you actually constructed that measure? So you need some alternative description, because this formula, well, doesn't tell you much. And this alternative description is given in form of the so-called Osterwalder-Schroeder axioms, and the measure should be also non-Gaussian. Yeah, so among the axioms we find the Euclidean invariance, reflection positivity, regularity, analyticity, ergodicity. And these should be understood as physical properties of the measure, which is somewhat given by this formula, or, well, also this includes other quantum field theories. And these are properties that somehow characterize the measure, so that you can work with that measure further and use it in physics. Okay, and then, well, you would like to see that it's really the Phi 4 theory and maybe not Phi 6 or something else. So you would like to compute the correlation functions. Yeah? And what we could also derive are the so-called Schwinger-Dyson equations. And this is a hierarchy of equations for the correlations functions. Okay. So this is the problem that we are facing today, but this problem has been already faced a long time ago, namely within the program of the constructive quantum field theory in the late of 60s, 70s, 80s, and so on. Yeah, and so this measure has been constructed. There are very advanced theories that also prove all the axioms, etc. I mentioned just some of the names here. the first, maybe second first, and then I would like to mention the paper of David Bridges, Jörg Fröhlich, and Sokal, because this has some similarities to our result. Namely, this was also a very simple construction of that measure. They come from a lattice approximation, as we do, and well, I will discuss a little bit more about it later. Okay. So now the question is, how can we actually construct this measure using PDE methods? So far we haven't seen any PDE here. But such a program was proposed in 1981 by Paris-Sivou. Namely, they suggested to study the stochastic quantization equation. This is the PDE that we see here. On the right-hand side, the forcing, this is a space-time white noise on R+, so this stands for the time variable, and then we have R3, this is the space variable. Yeah, so you see, in comparison to the previous slide, we have now this fictitious stochastic time, yeah, artificial time variable that we use in this dynamics. And the idea why it should actually help with the construction of the measure is that, at least formally again, the measure on the previous slide is the invariant measure of this dynamics. Yeah, so this tells you, well, if I solve my equation, I find a solution which is stationary in time. Stationary means that at each time the push-forward measure, the law, is the same. Yeah, so this would be the invariant measure, and at least formally this is given by that expression on the previous slide. So you would like to follow maybe this direction. Construct solutions first, then study the long-time behavior, prove existence of an invariant measure, and then maybe derive some of the other properties. So this is not exactly what we are going to do in this talk, but we will use this dynamics in order to construct the measure. Okay, and so now we have this equation, and the question is, well, is it actually any better now? Or why should this help us? So if you think about it, the right-hand side is very irregular. I said this is space-time white noise. And this can be constructed as a random distribution of regularity -5/2. So you see this number -5/2. This is also what we saw today in AJ's talk. That was the degree, how he called it. Okay, so this is a distribution. And what we also saw in AJ's talk was that for parabolic equations, this is also the equation that we have here, the solution should be 2 degrees of regularity better. These are the so-called Schauder estimates. You could also see it basically from the equation right away, because you see Laplace of the solution is kind of proportional to the white noise. So the solution itself has to be 2 degrees of regularity better. So these are the Schauder estimates, and then it means that I expect my solution to be also a distribution with regularity -1/2. So this kappa, this is just an arbitrary small but positive constant. Okay, and well, of course you recognize again the regularity of the Gaussian free field. So far nothing happened really. There are no big surprises, no magic is going on. But we hope that still this PDE could help us somehow. So why is this problematic? We see it already here, right? There's the cube in the equation. If the solution is a distribution, we don't know how to multiply distributions in general. So that's the reason for renormalization, and that's the reason why this problem is really difficult. Okay, but I claim that we have gained something. As opposed to the previous slide, now we have the dynamics. So, well, if you like PDEs like I do, then you're happy. But not only that, we also have the Gaussian noise on the right-hand side. So suddenly we have an object which we know very well, and we can do explicit computations with that. This is also what we saw in AJ's talk when he was building all these trees. So these are based on this Gaussian random variable here, and we can really do these computations and the renormalization explicitly. So this is something that does not appear on the previous slide in the formula for the measure. But here, when we write down the dynamics, we somehow gain this Gaussianity that we can use in our computations. Okay. So here is the wish list, what we want to do. We would like to study this equation and we would like to construct this measure. Namely, we want to have arbitrary mass, arbitrary coupling constant, and using the dynamics, we would like to construct something that could be called quantum field theory. We will also prove that the measure is non-Gaussian, and we are also interested in the axioms. Because, well, the equation would give us maybe some measure, but to have a meaningful limit, we want to verify the physical properties. So in particular, we will show translation invariance and reflection positivity, and then certain integration by parts formula, which allows us to write the hierarchy of the Schwinger-Dyson equations. I also would like to point out that our method applies to multi-component models, so we don't have any restriction on the number of components, and we can have arbitrary coupling constant. Yes?
Do you really need the positive mass?
No, that's somehow arbitrary, so we can somehow add and subtract linear term in the equation and it wouldn't change.
Even for the long time problem?
Yes.
The thermodynamic limit is not a problem in your approach. You can directly go to infinite volume.
Yes, I will discuss that. Yes.
Okay.
Yes.
What are the correlation inequalities you mentioned?
You mean here?
Yeah.
This may be a question for David. So this is because these are the axioms that we prove really by our methods, and then for proving the other axioms, we could proceed like in the paper of David and Jörg and use the correlation inequalities to derive these axioms, but this would again restrict the number of components here and the coupling constant. Yeah, so also here there is no miracle. Yes?
The one thing I don't understand is this fact about the mass. So if you fine-tune mass, it will become non-massive in the infrared limit, and you want to describe a highly non-Gaussian fixed point. Definitely that's not what you do. Just Ising, 3D Ising.
Well, like to
it is
have
there,
the
yeah.
conformal fixed point, but I guess
is there.
that's not it.
But it's probably not what we are doing, right?
No, it would be there. If you can do any mass squared, then it will be there.
It should be there if there's no restriction.
You won't be able to identify it.
You can't identify it, but it's there.
Okay.
Not a scaling limit we had.
No.
Okay, we'll see
Yeah, we'll see.
later.
Okay, and then similarly to the paper of David and Jörg, we are missing the rotation invariance because we start from the lattice, so we don't have that. Okay, so this is the wish list, and here is the strategy. So we start from a periodic lattice of mesh size epsilon and side length m. On this lattice, we consider the following Gibbs measure. So that's like a lattice version of that formula that I gave you on the first slide. Now we see now this is a finite product of Lebesgue measures, so everything is well defined. And in addition, well, the integral is replaced by a sum rescaled by epsilon to the dimension, and we see additional renormalization constants. And this is what we need because it will create the necessary counter terms in order to define the cube. So this is also what we have seen in the talk of AJ earlier today. Yeah, now this is a nice measure, and you can look at the corresponding stochastic dynamics, at the stochastic quantization equation. So this is what we do, and this is how it looks like. So you see, it's the same as before. In addition, we have the renormalization constants, and we are on the lattice. And the important point is that we study stationary solutions to this problem. So I start with a stationary solution. Basically, it means I start my evolution from an initial condition which is sampled from this measure. And I know that this measure is invariant for this dynamics, so my solution would be stationary at each time the push forward measure, the law, would be given by the formula over here. Okay, and now, well, the game is simple, or the question is at least simple. Well, we have these two parameters, and we want to send them to their respective limits. So that's like sending the ultraviolet and infrared cutoff away. To this end, we derive certain energy estimates. So we use a very old and classical PDE method, which is called the energy method. I will show you what the main idea is. And we derive estimates which are uniform in both of these parameters. So as a consequence, we may remove them simultaneously, and we obtain tightness of these approximate measures. Okay, and so once we have tightness, there would be a limiting measure, possibly many of them. So we need to pass to a subsequence, and then we prove properties of any accumulation point. So any such candidate limit of these measures would be a candidate quantum field theory, and we prove the properties that I mentioned earlier. So this is the strategy.
It could be trivial.
I also proved that it's not trivial. So it could, but it's not.
You cannot prove that for single coupling the limit is unique.
Yeah, I don't know how to do that.
Okay.
Oh, yeah, also it's not clear what would, how do you, in which class unique, or how do you formulate the class of measures? Maybe all the axioms?
There should be convergence of the sequence, I suppose.
Yes, yeah. So at the moment we have a subsequence here, yes. Okay, so first of all let me tell you a little bit about this energy method. Let us think about such a simple equation, and I say it's simple because the forcing on the right hand side is nice. Okay, so it's a very similar equation to our stochastic quantization, except for this fact that this is nice. And so what you could do in PDE theory to derive L2 estimates, well, you test your equation by the solution itself. In other words, this means, well, you multiply by u and you integrate with respect to the space variable. Or in yet another words, well, you differentiate the L2 norm squared. So whatever you call it, well, here I just multiply by u and integrate it with respect to x. So the brackets mean the duality product. Then I realized that for the first term, well, that's just the time derivative of the L2 norm squared. And then for the second term, here I can integrate by parts. So I get L2 norm of the gradient squared, and the important part is that there is a plus here. So that's a good term, which is on the left-hand side of my estimate. Yeah?
I suppose you do the pairing in the approximated version, right? This is just formal.
Yeah. Okay. I mean, this is a nice equation. F is nice. So
what I mean is, F is, is F not noise in this?
F, well, it is a nice noise.
Okay.
Yeah, but you're right. I will do it on the level of approximation where everything is nice. So actually there even this assumption applies.
You're doing it on the lattice.
Yes.
It's only finitely many equations here. The white noise is just an independent random variable for each lattice.
Yeah, but this is not on the, is this equation on the lattice or in the equation on the continuum?
Lattice.
Well, this is just a simple example. It doesn't really matter. So the point is, here you may think of an equation on the full space or whatever, but the point is that this one is nice. So, in other words, there is no problem in multiplying the equation by the solution, or you think formally. And the way we really do this computation later, we do it on the lattice when everything is smooth. So then it's rigorous. Okay, and then I have the massive term, and here you see this is immediately the L2 norm. And again with a good sign, so it stays on the left-hand side. And from the cubic term, I get L4 norm. So here I have already set the coupling constant to be 1. And you see what matters is the sign of the coupling constant, because I want this term to be here on the left-hand side of the inequality. Okay. And then we are left with the right-hand side, and this is what we should estimate. We are aiming for some uniform estimates for our solution. So, well, here we have the duality, and there is now several possibilities how to estimate this term. Here I have chosen one. I take L2 norm of the solution, L2 norm of the forcing. And now you realize, well, this is good, because I have also L2 norm here, so I can somehow try to absorb this one to the left. And that's what I do. So I use the Young inequality to separate these two terms. This is where it gets me, and I gain a small constant delta. And now you see if delta is sufficiently small, namely smaller than the mass here, I can absorb this term. And I end up with having only a bound for the forcing on the right hand side. And now you remember that I wanted to work with stationary solutions. Okay, so I assume that U is stationary. So at each time the law remains constant, meaning if I take expectation, this expectation does not depend on time. So the time derivative is 0. So this is now very convenient because I don't see this term anymore. And I get a bound. So all these terms have a good sign, they're on the left hand side, and on the right hand side I have only the forcing. To summarize, using this method, I have derived some moment estimates for my invariant measure based on the forcing only, based on the dynamics. I haven't used any formula that I might have for the invariant measure. So maybe I don't have any formula for the invariant measure, but still I get some moment estimates for the invariant measure here. And you also see that, well, this L2 bound, this was not the only possibility, because I have a duality, so I can use different function spaces, and I have also more terms on the left where I can absorb. In particular, if I want to use the L4 norm, I can estimate like this. If I want to use also the gradient, I could even have f as a distribution. So this is also what I plan to do for the stochastic quantization. And these are basically, I mean, this one, that, and that. These are the three estimates that I'm allowed to do. Because on the left side of my inequality, there would be these three terms. So that's what we want to do now. But as we already realized, our noise is not very nice. So we need to work a little bit harder to somehow get to a setting where we can apply this method, because immediately I cannot do that, but I have to somehow, well, tune my problem so that this method is applicable. And in order to do that, we use the paracontrolled calculus. So I would also like to explain the main ideas of that. So I have told you there is this problem of multiplying distribution. So this is what we are all talking about all the time. And one idea how to tackle this problem is to really study very precisely the structure of the product. And you separate different parts that behave differently and that require different treatment. So to this end, we consider the Littlewood-Paley decomposition. So f is a distribution, and here I write it as a sum of the corresponding Littlewood-Paley blocks. And I do the same for the other distribution here. And now, well, I look at a product of these two distributions, or you think of smooth functions, for instance, and you try to somehow, well, decompose this product in different parts. So I just plug in the Littlewood-Paley decompositions, and now I compare what happens if I and j have different values. And if you try to do so, well, you realize that there are somehow three kinds of behavior. The first one is when the frequencies of f, so this parameter I, is much smaller than j. In this case, the large frequencies will be somehow given by f, and as a consequence, the irregularity or regularity would be dictated by the distribution f. This is somehow the intuitive idea. Yeah?
So this Littlewood-Paley, can I think of Fourier series or something?
Yeah, exactly. These are projectors in Fourier space. Yeah, so you project, each of them projects on frequencies of size 2 to I. Yeah, okay. And then you have the symmetric term here, namely where the frequencies j are much smaller than I. So here the irregularity will be dictated by the distribution g. Okay, and then you discover a third term, and this is where the frequencies are about the same. Yeah, here some resonances can appear, so this is what we put in this third term. The first two are called paraproducts, and the third one is the so-called resonant product. And now the point is that the first two are always well defined, so you don't have any problem constructing these products, no matter what the regularity of the distributions is. But they might be very irregular. In particular, for instance, here, if g is very irregular, even if f is a function, this would be irregular. This would be a distribution. But it is always well defined. And then we have the third term, and this is not always well defined. So this is only then well defined when the sum of the two regularities is positive, strictly positive. So this is really the term which causes the product of two distributions not to be well defined analytically. Yeah? So this is a term where you need to do something. But if it is well defined, then it is function valued. So then it has positive regularity, and it's a nice term. Okay, and we use this decomposition somehow to track down the difficult terms and treat them, each of them, differently. Okay, so now let me move back to the stochastic quantization equation. So somehow the strategy is clear. I would like to use this energy method, but I cannot at first. So I would like to decompose my problem somehow so that eventually I arrive to some equation where this assumption nice is satisfied, and I can apply this energy method. Okay, so here is our equation again. I dropped all the m epsilons here, but they are there. So we are on the lattice. And I would like to study this equation directly on the lattice. Okay, and so now you remember the talk of AJ. So I would like to do something similar. Find a suitable decomposition. Yeah, and I also follow the same idea that this nonlinear equation, it is a perturbation of the linear problem. Namely, if I forget the cubic term, somehow the nonlinear equation shouldn't be too far. What I mean by that more precisely is if I define x to be a solution to the corresponding linear equation, then I could write phi as a sum of x plus something, plus eta, some remainder, and the hope is that the remainder is nicer, that it has better regularity. Yeah. So that's somehow the point. Now let us think a little bit more about the regularities that we have here. So I already said that the space-time white noise is -5/2, and we had the Schauder estimates before. So we know that the solution would be two derivatives better. Yeah, so -1/2 minus kappa. So we are back to the regularity of the Gaussian free field, of course. Okay, and so now the question is whether this eta is really better. So well, what I can do, I can use this expansion, this decomposition, and plug it in the equation. Now the way the part x was constructed is that the noise cancels. So somehow we want to eliminate the most irregular term, and this is exactly how we do that. So in the equation for eta, we don't see an xi, it's no longer there. What we see, well, we use this decomposition and plug it inside the cube, and we develop the cube. So I would have x to the third, etc., all the other terms. Now, this problem of multiplying distributions is still there. I mean, I cannot just write down x to the cube, as we know, because this is a distribution. But there are the counter terms, namely those coming from this renormalisation constant. So what we see here is the third weak power. So that's exactly in the computation we would see x cube and the right counter term for that to obtain the third weak power. And the same is here for the x squared, so this is also the weak power. And now the question is this actually any better? So somehow the most irregular term here is -3/2, that's this one. So it is indeed better, so we might be happy, but well, then you think, wait a moment, on the other hand we have some strange term here and we gained more and more products. Are these now well defined? And we realize that no, they wouldn't be well defined. So this suggests that we should somehow go further in our expansion, and we should have the next tree appear. So now what AJ would tell us, or maybe Lorenzo during the first workshop, well, you again remove the most irregular term. So again, you construct a new random variable. So this is the same notation that AJ used, except for the minus. And so it solves the linear equation with the third weak power on the right-hand side.
Where is A here? From
Here?
the first equation it disappeared.
Yes, yeah, that's the renormalisation constant, which I used already here to create, yes, to create the weak powers. Yes. So this minus 3a phi, this is exactly the counter term that I need to get this cube here and the square. Yes, thank you. Okay, so so Lorenzo or AJ, they would say, well, remove now this guy. But we do it a little bit differently because we are really aiming for this energy method, and if we just removed this term, it wouldn't work. So I take one step further and I remove also part of this one. And this is what we can see here. So I define y to solve again a heat equation. Also the third weak power is there, but in addition I include such a term. So what I mean by this, I take the Littlewood-Paley decomposition and include there only those frequencies that are larger than some constant capital L. So somehow the most irregular part, and also you see the paraproduct here. So this is really the most irregular part of this product here. And I want to cancel it as well, otherwise it would somehow bother me there. But now you see that it's different in the sense, well, this is not just an additive noise on the right hand side, the solution appears also on the right hand side. So this equation has to be solved via a fixed point, and that's why I have chosen here only the large frequencies. In other words, I can choose L sufficiently large such that the Banach fixed point argument for this equation works. And this way I obtain the next term in my decomposition, and I define phi to be x plus y plus the other phi. And now I write down the equation for phi. This is how it looks like. And well, I have singled out again the difficult terms. So these are coming from this product here, one paraproduct and the resonance term, and then, well, there are other. But these are better, and there would be some renormalizations needed. We would need to construct other stochastic objects, but somehow, well, let's not bother with them. And so now this is the equation where I want to apply my energy method. And so you would do the power counting and try to check whether it works.
L, does it depend on epsilon?
No. L would only, I mean, it's true that there are m epsilons everywhere, but it would depend on the norm of x squared, of the second weak power, but which is bounded uniformly in m and epsilon. But it's random, and that doesn't matter. Yeah. Yeah. But the constant L would not depend on m and epsilon. Yeah?
So you don't seem to have a small parameter in front of your cubic term. What makes it a contraction?
No, this is additive. So if I take like a fixed point map, I take a difference of two solutions, this would cancel. Yeah, because this does not depend on y. This is like additive forcing. So it's really only this term because there is y on the right hand side, so this is what bothers me. This is where I need to get the small constant. Yeah. Okay, and so now we would like to do the energy method. So you remember, we want to test the equation by phi, so we would get the time derivative of the L2 norm. You remember we are on the lattice, so this is the L2 space on the lattice. We have the fourth power, and then for the rest I keep the testing. So I multiply the equation by phi and I integrate it. So here integral means a sum because we are on the lattice. Okay, and so now if you think about it, there was still this assumption, nice. So is that true here? Well, I expect this term to be -1 because that's the second weak power. And we know the Schauder estimate, so again I expect my solution to be 1 minus. And you see that it's not enough actually to have this term well defined. Yeah? And similarly here, I expect phi to be only 1 minus, so this resonant product, which is well defined only if the sum of the two regularities is positive, this is not well defined. So I still have some problems. Yeah? But there are, well, two simple tricks that we used. And the first one is an observation that this term and this one, they're basically the same. Yeah? In other words, if I take the difference, and somehow it's like looking at the error if you want to change from one term to the other, this is some operator which depends on phi, on the x squared, and on phi. And this can be controlled provided the sum of the three regularities is strictly positive. And now you see that I really gain something, because for instance this resonant product alone would require the sum of the two regularities to be positive, which is not true. But if I have the second phi to help me, then the sum of the three regularities is positive. And well, the reason why this works, there is this additional duality. So somehow without the duality, without this integration, these terms are not well defined, but using the duality, they kind of look the same. So they do not cancel, but they look the same. Okay, and so now the idea is, well, these two look the same and they diverge. But on the other hand, we have this term on the left which also diverges. So I want to have them compensate each other. So I put them together, I take the Laplace term together with these two, so this is what I obtain. And I consider an elliptic paracontrolled ansatz. So I define psi, which is then supposed to be better than phi, as follows. So there is the Laplace, here I have also the Laplace, and here I have the paraproduct. So it's basically, you take this term, plug this in, and you complete the square. Because that's why there is this 2, because that's like the mixed product in the square. And once you do that, you are actually able to overcome the problem of these terms not being well defined, and we are still able to obtain the estimates. So this is what we are going to see here. And yeah, of course I cheated you a little bit, because we are on the full space. And there the noise grows at infinity, so we have to include weights to somehow push it down. So I include polynomial weight of this form which decays at infinity. So instead of testing by phi, I actually test by phi rho to the 4th power. And otherwise I do exactly the same computation as we saw on the previous slide, and this is what we obtain. So here we have the time derivative, the L4 norm. We get some regularity of phi, but you see it doesn't have the full derivative. And we have bound for psi, and you see that psi actually has the full derivative in L2. This is what we expected. So it is somehow better than phi. And on the right hand side here, this is a polynomial of weighted norms of all the stochastic objects that we had to build. So here there are the first 3 that we saw, but there are others that are needed. And what we obtain here is then a polynomial whose coefficients do not depend on m and epsilon. And also the norms that we consider here of the stochastic objects, they can be bounded uniformly in m and epsilon. So this is the basic energy estimate that we get. And what I would like to point out now is that this problem of the resonant product that we saw on the previous slide, it is still there. So this resonant product is still not well defined, and even for psi, which has better regularity, this is not well defined. In other words, if I were to pass to the limit now in the towards the continuum stochastic quantization, I cannot do that because I cannot control this term. But somehow the remarkable fact is that I don't care, because at this point I don't care about the stochastic quantization anymore, because I have some uniform estimates, and those are estimates that are sufficient for constructing the measure and proving that it is non-trivial and the axioms, etc. So somehow at this point I do not care really that maybe this term is not well defined. So maybe the way to see this approach, it's kind of an analogy with what is called PDE weak solutions, when an equation is satisfied in a suitable duality sense. So here would be like you would need some kind of paracontrolled test functions, and then the equation can be formulated. And this is opposed to our previous paper with Massimiliano, where this is what I would call strong solutions. So there, well, we got stronger estimates than these, but also the decomposition was much more complicated and there was much more work. So somehow our goal in this second paper was to have a very simple approach which is sufficient for constructing the measure but maybe isn't enough for passing to the limit in the equation. However, one could prove a little bit more regularity. So what we do are like mild Schauder estimates, only somehow in the L1 scale, and then we can make sense of the resonant product, and we can actually pass to the limit in the equation. And this is actually what we need to then derive the integration by parts formula, as well as the Schwinger-Dyson equations. Okay, so this was the basic estimate, and now this is the main theorem. One more remark. So our decomposition was like this. Phi was stationary, x was stationary, but y, as it solves this strange equation, this is not stationary. And as a consequence, also this guy isn't stationary. So somehow this idea from the very beginning of my talk in the energy estimate that the time derivative cancels, it actually doesn't apply to my energy estimate, yeah? Because this guy is not stationary. But one can play around a little bit. I move to the stationary one, so x is still stationary, this 3 would be stationary, and somehow this non-stationary part in y I include here. So now this new zeta is stationary, and actually everyone in this expansion is stationary, so I can play around a little bit and use my energy estimate anyway. And so then what we get is that the family of joint laws, here I have all the stochastic objects and I have the fields, when they are evaluated at some fixed time, this family is tight. And I also preserve all the estimates that I proved. So if I define now zeta, basically to be this, to have that decomposition, then any limit measure satisfies these moment bounds. So namely, the fields live in h minus 1/2, and we have all the moment estimates. And for zeta, we have the L2 norm also with the moments. We have the h1 minus 2 kappa norm. And this is basically coming from the L4 norm that we saw. And so now, this is what gives me the important information about the measure. So I have this actually gives you bounds for all the correlation functions. And in addition, I have this decomposition, and I know that somehow the remainder, the zeta in this decomposition, is nice. It is very regular. And this is what I can use further in order to work with this measure. Okay, so let me tell you a little bit more now about this non-triviality. Well, regarding the axioms, there is the reflection positivity and translation invariance. It's not difficult to prove them since we came from the lattice where these axioms hold. So I would like to focus more on the non-triviality, and I denote nu any limit of these discrete Gibbs measures. So it's basically projection of this measure mu on the first component. And now I want to prove that this limiting measure nu is non-Gaussian. And the way to do that is you look at the connected 4-point function, which is defined as follows. So I pick 4 points in R3. Here I have the correlation of phi x1 till phi x4, and here I have the connected correlations, all of them. And now if phi was Gaussian, or if the measure was Gaussian, then the connected 4-point function is 0. So the goal is to show that this is not 0. And now I remember my decomposition. So the field was given like this. Now the first term is Gaussian. However, the second one is not. And now the hope is, well, that this zeta is much more regular, or, well, sufficiently more regular, such that it cannot cancel the contribution of this 3. So that overall this would remain non-Gaussian. And so for that, I need to use my moment estimates from the previous slide. And this is how it works. So I should prove that this distribution is not 0. So I need to find one point where it is non-zero. And I take Ki to be the kernels for the Littlewood-Paley projector. So this is a projector on the scale 2 to I. Now the 4-point function is a distribution in 4 variables. So I convolve 4 times with this kernel. And then I evaluate these convolutions at 0, 0, 0, 0. So after all, what I get is just this expression. And this defines a multilinear map on the fields. Okay, and now I remember again my decomposition and I plug it in. So the first term, this is where I have only x, 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 x. This is Gaussian, so this one is 0. But then I have the term which is the second most irregular, and that contains this tree. This is now not Gaussian anymore, so I expect this to be non-zero. And then I have all the other terms, so there is some remainder. And now I estimate every term in the remainder, and I show that this is smaller than 2 to 1/2 of I. But on the other hand, for the second term on the right-hand side, I can do explicit computations. So that's again this fact that I have 3 Gaussians here, and this tree is also built from these Gaussians. There is the weak power and then once more integrated. So actually explicit computations then yield that this term is proportional to -2 to I. And that's good, because you see these are really much smaller, at least if I is sufficiently large. And from this you can conclude that the 4-point function is not zero. And this gives you the non-triviality. Okay, so let me now say also a little bit about the integration by parts formula and the Schwinger-Dyson equations. If we start from the discrete measure again, so this is...
I still ask about this non-triviality, but there are this AM and BM are somehow contained.
They are included in the stochastic object.
The limit where you go somehow with M to infinity, what this AM are doing somehow, and with epsilon to 0 somehow.
They are used to construct the stochastic objects. So they are already hidden in the uniform bounds that we have for the stochastic objects. So for instance, in the first decomposition there would be x cubed, and then somehow this term, even though this diverges, that's the counter term. So this would, this would converge to the weak power. So these constants are already hidden in the stochastic object. And also for the other constant, this is needed there to construct some other stochastic objects that we need. Yeah?
It's a little surprising that you can claim that the 4-point function is non-trivial independently of the size of the coupling constant.
Well, this chicken...
No, maybe it's true, but I find it a little surprising.
What do you mean? Maybe these constants here depend on the coupling constant. I think in the estimates we could have like uniform bounds if the coupling constant is sufficiently small.
Coupling is going to 0, so that's what's happening.
Yes. But otherwise these bounds, they would depend on the coupling. Probably.
Mm-hmm.
Yeah. So we work with a fixed coupling constant, and then we derive the estimates. So I don't say it's like uniform in the coupling constant. No. Okay. So if we look at the discrete measure, this is the formula again. So here, well, that's just a product of Lebesgue measures. So there is an integration by parts. Namely, if I take a functional on the fields, for instance, something like that, so a function where the field is tested by some test function, and maybe I could just think of a product. And so if I look at the derivative, I can integrate by parts, and then the derivative hits the density here. So this is what I obtain. So that's just integration by parts for the Lebesgue measure. And now what we would like to do is to pass to the limit, to obtain an integration by parts formula for the limiting measure as well. But of course what we see here is the cubic term and the corresponding counter terms. And I told you that I'm not able to pass to the limit in the equation. And this is basically passing to the limit in the equation. So in order to do this, I need to prove a little bit more regularity. Because as we saw, there is this resonant product which is not well defined under these estimates that I showed you. But there is actually another problem which is even more substantial, namely that the third weak power can be constructed only as a space-time distribution. But here we work under the invariant measure, so well, there is no time anymore. This fictitious stochastic time is not there anymore. And actually what we do in order to handle this term is we reintroduce the stochastic time. So actually in our integration by parts formula you would see the stochastic time again. And this is how it goes. So I use this notation for the cube. This is now what appeared on the right side of the integration by parts formula, and I want to pass to the limit. And so now, well, as I have these problems with the space-time distributions, I want to reintroduce the time. So I remember that, well, this is an expectation of my approximate solutions at some fixed time t. And this expectation does not depend on time because of the stationarity. Okay, and so now I take a function h of time which integrates to 1. So I can just put this integral of h here and I could write it this way. And what I gained is that now I have the time there again. And so, since this cube is actually expected to be only space-time distribution, I could use some kind of duality to control the integration by parts formula. Namely, here this would be a distribution in time, but this guy would be somehow a Helder function in time. But that means that I have to prove stronger estimates than what I showed you before. So, actually we now somehow upgrade our tightness argument, and we prove tightness for these fields as stochastic processes. You remember before, I only evaluated them at fixed time, and that was my tightness. And that was sufficient for the non-triviality and the axioms, etc. But here, I need some regularity, some time regularity, in order to control the cube here. So I establish better regularity of my solution, namely also some Helder continuity, okay, in some negative Besov space, but that's not very important. What is important here is the time regularity. Yeah, and as a consequence, well, included in this is also higher regularity of the field in space, such that I can make sense of the missing resonant product. Yeah, and so under this new regularity, I'm able to pass to the limit here, and I obtain the following integration by parts formula. So there is still the Laplace term, and now this is what I get from the cube, and I have a formula for this kind of third weak power. Namely, it is given by my expansion, so we see this cube there, and then, well, it's basically doing the same decomposition and plugging it inside here again. It's a similar computation as what we did before. Yeah, so you get somehow an expansion, there is an explicit formula, and we have a control of every term in this expansion. Okay, and this is then what allows you to formulate the Schwinger-Dyson equations, because we can also construct this term somehow in the spirit of the operator product expansion. This is what we saw on Monday in the talk of Malek. So basically here it means I evaluate the fields at different points, and then I want to bring the points together. So we do it with, again, Littlewood Paley projectors, where we take the small frequencies, and then as we zoom out or we send n to infinity, this would converge to this limit. So that's somehow another approximation of this term that appears in the integration by parts formula. Yeah, and then basically you just plug particular functionals in the integration by parts formula. So here this means that this guy is not there. Yeah, and then we get a relation for the endpoint functions in terms of other endpoint functions.
So slightly puzzled by this, the phi cube that you have on the left-hand side, that's only recorded, right?
Well, that's...
Well, so it's this.
What
Is
what-
it?
This is the formula for that. This is...
Do, but you see, it's not really recording. It also has to include the mass counter term, which depends
Yeah.
on the coupling constant. And I wish to understand how they see which mass counter term to choose in their construction.
It comes, you see it from the expansion. Well, yeah, like you take this expansion and you plug it inside the cube, and then you see the counter terms, they would come from here, and you have to combine them in the right way to construct all the trees. Yeah. But I actually wanted to end my talk here. Thank you very much.
Thank you for the talk, and I'm sure there are questions. Many. Maybe since you were already asking.
A short one. I didn't understand why you need a fixed point theory. The equation in question appeared to be linear to me, so.
Yes, but this one.
Well, it's linear in y, right? So why can't you take the second term on the right side to the left side and then invert the operator? It will be a stochastic operator.
But you would get a short time, or you would need something to tune, some parameter to tune to get the contraction.
Just invert a certain operator.
You mean together with this one?
Yeah.
Okay.
This product is
Yeah, so you would have some paradifferential operator.
still linear in y, you are
I
saying.
think so, yes. Linear
It's
in
true.
y, so. Anyway.
You would need a theorem for that, probably, anyway.
Yes.
to
well,
invert
yeah,
that
of course
operator.
you can invert an operator by, but it's
Yeah.
just a
And what is
series
actually the
expansion.
space in which you take this fixed point?
Right.
Perhaps you are just using, perhaps the fixed point is simply the result of that.
Exactly, that's right.
Yeah. So the space where this y lives, so it somehow continues in time.
Some hurdles.
1/2 minus kappa. So this is the B infinity space. So this is where we take the fixed point. So I don't say that this is the only possibility, but for this the proof is fairly simple.
Can you construct correlation functions with a stress energy tensor?
Could you tell me what a stress energy tensor is? So maybe the answer is no.
I'm asking because if you had that, you could write down a water density for the preservation of rotation invariance, which apparently you're missing here. That's a standard way in quantum field.
You are talking about vector case, where the...
What?
You are talking about vector case.
No,
where
I'm
the
talking about one component. The stress energy tensor is the Noether current for space-time translations and rotations. And it's an operator which is bilinear in the gradient of phi, so it's like a grad phi squared. And if you compute its divergence inside a correlation function, it has to obey a specific identity to guarantee rotation invariance of the correlation function.
Okay.
If it doesn't, you can oftentimes then repair the theory by adding a further counter term, which you could read off.
Okay.
Since you can't.
So right now I don't know, but thank you for the suggestion. That's
I think there's questions anyway to Jörg and David also. So David.
Oh, I could say it slightly differently. So I don't clearly remember now how Lim and Jaffe proved Euclidean invariance, but I think it was something like this, that they would construct the model. I will translate it into these terms, right? You could construct a model for the lattice with two different orientations. In the continuum limit, you may be able to form. If you just for momentarily think of it as a perturbation of a Gaussian measure, but anyway, the idea would be that the Gaussian measure for one orientation and the Gaussian measure for another have covariances.
No.
You could look at the convex combination of those two covariances
Okay.
and differentiate with respect to it. Maybe if you can control the resulting correlation function,
Okay.
you could perhaps get something.
okay. So yeah.
Maybe believe that this topic was a discussion because there are a number of other questions. Maybe.
And what about uniqueness of invariant measure?
Yeah, so I don't know. You would need to formulate somehow in which class are you looking for uniqueness. So if you look for uniqueness, unique invariant measure of the stochastic quantization, but in any case, yeah, we don't have anything.
I don't know if it is unique.
I don't know. Yeah.
No, it won't be.
And for large mass or something?
What you guess?
What David guesses.
Well, if you allow your physical mass to be sufficiently negative, I mean that parameter sufficiently negative, so it's quite double wellish, then
I know.
Well, I mean, of course, she chooses special boundary conditions, so she will probably get the superposition.
Well, she's on a torus.
Yes. So she gets the
Yeah, I mean, one thing you could do, I don't know whether you tried, is just to add a small magnetic field. And that will, if you add a small uniform magnetic field, then you'll have a unique state.
Mm-hmm.
But if you don't, you could get all kinds of things.
Yeah.
So, just to be clear, so you can do this construction even if m squared is very negative, right?
Yeah, because I could then add another mass on the left and somehow hide the negative one to the right hand side.
I don't know if you're allowed, but I mean, so that means that you must cover the massless case, right? But maybe you have no way of telling if it's massive or not.
That's right.
Mm-hmm.
Yeah.
That's right.
proposal. I think you should reinstall lambda, the coupling constant,
And trace it down.
because it's very unclear who depends on lambda among your counter terms. Counter terms will depend on the coupling constant.
Yeah, this would somehow get multiplied by lambda.
Actually by lambda squared.
When m squared some value that
So what is the reason you use the lattice instead of some smoothing approximation? Is it only for the integration by parts formula?
Well, and the reflection positivity. So for instance, there was a talk, I think on Tuesday, of Seiichiro Kusuoka, and the underlying idea was similar. They started from some invariant measure of some regularization, but they only modified the cubic term. And at the beginning, we tried to do that as well on the full space, but we ran into some troubles with the weights. So then we thought we could add higher order Laplacian as a regularization, and this would work as well, but for that you don't have the reflection positivity. So that's why, well, then we chose the lattice, and I think it seems to be a very natural approximation.
But you have no Euclidean invariance.
Yes. Not yet.
I have just a technical question. So actually I don't quite understand why you introduced the equation with the y there instead of doing the same decomposition that everybody else has done before. That's on the slide. Why do you...
Yeah, I know. Well, so it's somehow, if you didn't do that, you would have x squared times this 3, because you would only subtract that 3. And then, so that would be irregular, and this duality wouldn't help you with that. Because we wanted on this equation already use the energy method, and this term would be more irregular than this one. Yeah, so here somehow, even though, so this one is the most irregular term, but if the x cube integrated would be there, it would be more irregular. So it's like we get rid of one irregular term more.
So maybe we have a 5-minute break and then continue to the next talk.